Now we'll be doing capillarity and height of liquid in a capillary tube, which is very important and significant. सभी एग्जाम्स में ये आते ही आते हैं. If we look into it, then class 11th capillarity and height of liquid in a narrow tube. So capillarity basically means the phenomenon of rise and fall of liquid in a narrow tube of uniform cross section is called capillarity. जैसे हमारे ब्लड का जो ट्रांसपोर्टेशन होता है बॉडी में, that is through narrow tube like structure which is called arteries and veins. प्लांट्स में जो ट्रांसपोर्टेशन होती है मिनरल्स की और वाटर की, that is through xylem and phloem. These are all examples of capillarity. When we talk about this capillarity, then there are two terms associated with it. First, it is the meniscus and angle of contact. Let us take two fine bore of capillary tube. In both, we fill some liquid. In first, it is filled with water, and second, it is filled with mercury. Then, surfaces in both, if you observe with the help of what we call microscope, then one, next, the second one filled with mercury, ये कॉनकेव जैसी होती है सरफेस, तो इसको मेनिस्कस बोलते हैं. और इस मेनिस्कस को अगर हम ऐसे टेंजेंट ड्रॉ कर दें विद द सॉलिड सरफेस एंगल, यहाँ पे टेंजेंट ड्रॉ कर दें तो वी हैव एंगल इनसाइड द लिक्विड. सो द एंगल made by the tangents drawn inside the liquid surface with the solid surface is called the angle of contact. Angle of contact. और पानी के केस में, वाटर के केस में बहुत स्मॉलर वैल्यू होती है थीटा की, जबकि मरकरी के केस में ये ऑब्ट्यूस होती है. इसी रीजन से मरकरी कॉलम जो है किसी कंटेनर को वेट नहीं करता है, जबकि वाटर वेट्स द कंटेनर. नाउ we want to find the formula for the height of liquid in a capillary tube. For that, we can have a diagram. If we can assume a beaker like, and inside the beaker, we are putting a narrow tube like, and the one end of the tube is touching the base of this beaker. Then we observe that if it is filled with water up to this, then water rises by some amount, let's say by h, above the normal level of the water inside it. And then if we try to find the formula for height, what we do, first let us have this as the spherical bubble type structure at the top of this tube having certain radius capital R, and we take small radius and height of this liquid of this tube. This angle is theta. So If it is a liquid drop kind, then we know the excess pressure inside, right? So we'll be using this formula, excess pressure in a liquid drop is 2T by R. One, we also know atmospheric pressure P as H rho G. So if we equate 1 and 2, we get H rho G as H rho G as 2T upon small r. Therefore, what could be H? It would be 2T upon R, rho and G, which means यहाँ तक रिमूव करना पड़ेगा, फिर थोड़ी एरर आ गई. So at the top of the liquid column, if we consider like a size of liquid drop, then we know the excess pressure inside liquid drop is how much? It is 2T by R. Excess pressure is 2T upon this R1. And we also know that the atmospheric pressure P is given by H rho G. So if we equate them, then we get H rho G is equal to 2T by R. Therefore, height becomes 2T by capital R rho into G. Now from the diagram, if you take cos theta base by hypotenuse, so small r upon capital R, which means capital R can be small r by cos theta. And therefore, we modify it like H is equal to 2T upon, for capital R, small r upon cos theta into rho G as it is. So it becomes 2T cos theta divided by R, rho and G. This becomes our formula. And this height is inversely proportional to the radius of this capillary tube. So narrower the tube, more will be the height of liquid and vice versa. Somewhere it is also written as Jurin's law, Jurins, Jurin's law, right? So it's all about this height of capillary tube.